Thank you. Thank you for inviting me. Yes, I will talk about, the goal of this talk is to present a new coding technique, which I hope at least could be interesting for you. For me, it is interesting in several reasons, because first of all, it works in a very, very general setting. So the coding technique I'm going to present to you will first generically create a ground model over which to code, and then in the second step, just do the actual coding of, say, the non-stationary ideal. And this is kind of new, because usually forcing arguments or coding arguments in set theory use some definable ground model, say L, use some objects in L, alter them with forcing, then you obtain a generic extension of L called L of G, say. And in that L of G, you can define L, you can define the old object you manipulated, and you can read off the pattern, the new information you encoded into. But this method I just said, I mean, this can work for other inner models for larger cardinals as well from time to time, if we work carefully. I mean, it gets harder and harder the higher we get up in the large cardinal hierarchy, because the inner models just become more complicated. But this technique I'm going to present to you is different from that, because we can just start with an arbitrary V, as long as there are sufficiently many inaccessibles in it, basically. That's it. Yes, and this means that we can obtain basically this result, because yeah, you will see. So good. So the first definition is just the most basic definition. So the non-stationary ideal on ns omega 1 on omega 1 is saturated. We say if every sequence of stationary subsets of omega 1 with the property that the intersection pairwise is non-stationary, so we get an anti-chain, the power set of omega 1 modulo the non-stationary ideal, has length at most aleph 1. So it just said, put in forcing language, the Boolean algebra power set of omega 1 modulo ns has the aleph 2 cc. So this means that the non-stationary ideal is saturated. And what's interesting about it is that it has been normal ideals on regular cardinals behave differently on omega 1, and the non-stationary ideal is the crown example for that. So it has been noticed first by Steele and von Wessel that the non-stationary ideal can be saturated, as opposed to kappa, for kappa being bigger than aleph 1. This was the first, and then Martin's maximum, the Martin's maximum revolution came by Foreman, Megiddo, and Scheller. And Martin's maximum implies outright that the non-stationary ideal is aleph 2 saturated. But Martin's maximum, of course, needs a supercompact. So the optimal large cardinal hypothesis was found by Scheller around the same time. And the optimal large cardinal assumption is a Woodin cardinal, yes. Let delta be a Woodin cardinal, then there is a delta CC notion of forcing called P, such that the non-stationary ideal in the generic extension will be saturated, and the Woodin cardinal will be collapsed to aleph 2. And that the large cardinal assumption of a Woodin is optimal, this was later proved by Jansen and Steele. Okay, but I want to talk about not only about the non-stationary ideal being saturated, but about the non-stationary ideal being saturated in the context of definability. And we know due to Woodin that there are lots of, I mean, there are some very, very interesting results connecting definability of families of H omega 2 with, in the presence of the non-stationary ideal being saturated. So there are, I mean, we got Tmax forcing, we got the stationary tau, and these things, yeah, can be used to produce very interesting connections between these two statements. So, and the starting point is this following theorem of Woodin, that assuming that there are omega many Woodin cardinals, then there is a model in which the non-stationary ideal is omega 1 dense, which means that the power set of omega 1 modulo the non-stationary ideals, seen as a Boolean algebra, has a dense subset of size aleph 1. And this means, of course, that it's aleph 2 saturated, because we got this dense aleph 1 size subset in there. And on the second side note, I mean, it means that it's delta 1 definable over H omega 2 with the parameter this dense subset. Because we can just say some set is stationary if there is something in the family which is below it in the dense family, right? So it exists. So this is sigma 1, making stationarity a sigma 1 predicate. Pi 1, it's automatic anyway by definition. So, okay, so yes. And the question now, which is actually a question from Cy Friedman and Yushen Wu, is the question whether it's possible that if we of course the density, the omega-1 density of a non-stationary ideal is stronger. But if we just want to have the non-stationary ideal delta-1 definable and saturated, can this be obtained from less than omega many Woodins, right? Yes, and there are already, or there have been quite recently produced a couple of negative results which indicate that strong assumptions usually prevent the delta-1 definability of the non-stationary ideal. So this is the first thing I want to mention. So if the non-stationary ideal, for example, is saturated and the power set of omega-1 sharp exists, then the non-stationary ideal cannot be delta-1 definable with omega-1 as a parameter. This has been extended by Lücke, Schindler, and Schlicht. Assume that a Woodin cardinal and a measurable cardinal above it, then no subset of the power set of omega-1 which separates the club filter from the non-stationary ideal is delta-1 definable with omega-1 as a parameter. So this is stronger. And this is a quite recent result that if we assume the bounded Martin's maximum and a Woodin cardinal, then for any parameter, so not only omega-1, but for any subset of omega-1, the non-stationary ideal cannot be delta-1 X definable. Okay, but quite surprisingly, I think the above mentioned question whether we can have NS saturated and delta-1 definable has a positive answer. And this is the theorem its proof I want to at least sketch to you today. So that, we can basically, as already said, assume that V is just any universe with a ladder system on omega-1. This is something we fix in advance and will be a parameter. And T a full Suslin tree on omega-1. So we don't need a full Suslin tree. So you don't need to know what a full Suslin tree is. You can just replace it by, say, an omega sequence of Suslin trees, such that whenever you take finitely many of them out of the sequence and build the tree product, then the tree will still be a Suslin tree. A full Suslin tree implies such a sequence, but this is what we actually need. So we need omega many Suslin trees. And whenever we pick finitely many out of them and build the product, then there will still be a Suslin tree. Okay, so assume that now V is a universe with a Woodin cardinal, fix this ladder system, fix this full Suslin tree on omega-1, then there exists a model such that the non-stationary ideal is saturated and delta-1 definable with the ladder system and the full Suslin tree as a parameter over H omega-2. And if we restrict ourselves and do not start with an arbitrary model, but instead force over M1, the canonically inner model with a Woodin cardinal, then we in fact get the optimal parameter because we can define away basically the ladder system and the full Suslin tree. So assume that M1 exists and there is a generic extension of M1 in which the non-stationary ideal is saturated and delta-1 definable with just omega-1 as the parameter. And this is kind of optimal, right? So we can't get a better parameter than omega-1. This is probably something worth mentioning as well. So in fact, the coding method is more flexible and can be applied to any definable family as soon as it is preserved under CCC extensions. And by that I mean that X is, some element is in X in the ground model, then some element will also be in X as seen from the generic extension, the CCC generic extension. Okay. Good, yeah. So, now for the rest of the talk, I want to sketch at least how one obtains the result. So the coding method itself uses 3 different coding methods. It's a combination of 3 different things. The most important thing is this coding method invented by Anders Kaseda and Boban Veličković. And this coding method, in fact, will be used to force a suitable ground model. This is the thing I mentioned in the beginning, right? So we will use this coding to actually start with an arbitrary model and produce a very, very robust H omega-2, which is robust under CCC extensions and nicely definable. And from that point on, so we generically produce our H omega-2, and then from that point on, we just use CCC forcings. And we are in some sense in the same situation that I mentioned before, right? So this H omega-2 now will play the role, say, of L. We can find it in CCC extensions, and we can just do our usual coding things. We just need objects from H omega-2 in order to manipulate, right? And these objects will be Suslin trees. And killing them and specializing them will be CCC. So all these things go together very well. Okay, so this is the first coding method. The second one is just, just almost disjoint coding. In its most, I mean, given a set of reals in the ground model, then we can force with the CCC forcing, which is called an almost disjoint coding forcing, one small reel B. And this small reel B, together with a predicate for being a reel in the ground model, can define the big set of reals B in the generic extension. This is something we will use again as well, once only. And the last thing is, yes, the last thing is these sequences of Suslin trees. I mean, I mentioned already before that we obtain with the Casado-Veličković coding, we obtain this H omega 2, which is robust. Now we want to have objects in H omega 2 which we want to manipulate in order to inscribe, say, a predicate for being stationary. So we need many Suslin trees. Many Suslin trees we can kill and specialize at will. And by that I mean that we got this omega 2 length sequence of Suslin trees, and this sequence should be independent, meaning that whenever, just with the full Suslin tree as well, right? So whenever we take finitely many out of them and build their product, then the product will still be a Suslin tree. Consequence that whenever we have this long sequence of Suslin trees, we can just kill and specialize these trees with finite support and write an arbitrary pattern into it and still obtain and still end up with a CCC forcing with finite support. So that's the thing. Okay. Okay, so I start with a short and very, very insufficient description of the Casado-Veličković coding. To introduce it would be way too long. From now on, we start with an arbitrary model D. We fix this ladder system C on omega 1, which will be one of the parameters. Yes, exactly. Yeah. So one of the key concepts in Casado and Veličković paper is the following. So the isolated theory T. And this theory T is in some sense, I mean, one can think of it that if some model satisfies it, then this is in some sense a more robust way of talking about H omega 2. So the theory T consists of ZF minus, meaning ZF minus the power set axiom. Then every subset of omega 1 should be coded by a of almost disjoint reals F. So this is something I should add as well. So given our ladder system C, which we fixed in advance, we can of course compute easily an almost disjoint family F of reals out of it, right? So this will be the almost disjoint family relative to which all these almost disjoint codings will take place. The third axiom should be that every set of that model, everything should be of size less than or equal than Aleph 1. And then in the fourth line, I'm super hand-wavy. Basically, the fourth line, I mean, now the two most important things for the theory T are missing. But the problem is that in order to introduce them, it would take way too much time. So instead, I chose to just, I mean, do not define the theory T properly. Instead, just tell you what models of the theory T will look like and how they behave. Yeah? I should add probably that in the paper they assume instead of every subset is coded by a real, via almost disjoint coding, they, Casado and Veličković assumed Martin's axiom to be part of the theory T. This is too strong. If we have Martin's axiom in the theory T, then this would rule out the existence of Suslin trees. So this is a slight a slight change in their definition. But for the properties of the T models, nothing changes if we replace this. Yes, exactly. So and now a couple of properties all these T models have. So the first thing is that we can they in fact exist as soon as we have large cardinals in the universe. So given an inaccessible cardinal kappa in the universe V, there is a countable support iteration P of length kappa. Everything is proper, such that in the resulting generic extension, the inaccessible will be omega 2, and the H omega 2 of the resulting model will be a T model. That's the first thing. So they exist. And then there is this very, very impressive uniqueness property that basically, whenever we do have a T model, it's completely determined by its ordinal height, right? So this is very, 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 very robust in some sense. So whenever we have transitive models of T, both of course containing this always, I mean, whenever I talk about a T model, I always mean that the models are transitive of size Aleph 1 or Aleph 2 and contain the ladder system. So again, so transitive models of T containing C are uniquely determined by the ordinal height below Aleph 2, right? So whenever we do have two T models and both are models of T both contain the ladder system, yes, then there is only one. And the interesting thing is that this property is not lost even if we pass to an outer model. So if we pass to a stationary set preserving extension and look at the T models in that newer, in that bigger thing, then at least, I mean, the old T models from the ground model will still be the unique T models even for the generic extension. So nothing changes. So yes, I will later draw a picture. Yes, and the third thing I'm going to use is the generic absoluteness for CCC extensions. So whenever we do have a T model, or we are in a universe where there are plenty of T models, and we pass to a generic extension, which is just a CCC extension, we won't get any new T models. And this is used. This is super useful because now we can find basically the old H omega 2, because it will just be the largest T model in there. And everything else will, I mean, and if we extend the universe further with just CCC forcings, we can define the old H omega 2 of V via just saying I'm in the H omega 2 of V if and only if there exists a T model such that the T model contains X, and that's it, because of the uniqueness, right? Yes, and the fourth property, which is very useful as well, is that every T model has a definable well order on it. A very easily definable well order on it, using this ladder system C. And this we're gonna use as well. So and this definable well order even lines up. So we got an L-like picture. So if you think of L and all the initial segments of L, I mean, of course, all these initial segments they do have this definable well order in there. And if you pass to a bigger initial segment of L, the well orders will coincide, right? I mean, the lower one will just be an initial segment of the well of the larger one. And this is exactly the same situation here, right? Okay, so and from now on, I'm done with this omen. And I want to switch to the blackboard. So I have till 5 minutes, what? 10 minutes, good. Good, so okay, so it's already said. So we obtain, the T models give rise to the following picture. So assume that we have many inaccessible cardinals. So assume I less than alpha, say, and alpha should be, I don't know, is a sequence of inaccessibles. Then we can start to produce, as just mentioned before in property 1, we can use these inaccessibles to produce these T models. So start a proper iteration of length to produce T models. So we do have here our first inaccessible kappa 0, and this should be our ground model, say. And now we extend it, make it bigger. Kappa will now be the omega 2 of, say, VG0, where G0 is the, you know, the first initial segment of the generic extension. This will be now the H omega 2, say, of that extension, and it will be a T model. Then we do have here our kappa 1, our next inaccessible, and we can start all over again and turn that into a T model. And of course, I mean, so we do have this well order on the T model. We do have a well order in here, but everything which is new will sit in terms of the well order on top of that thing. And we can continue. So we'll just, you know, we generically produce here a very nice hierarchy on H omega 2. Just produce, just using lots of inaccessibles, and we are in that situation because we care about the non-stationary ideal being saturated, meaning that we assume a Wooding cardinal anyway. So we have plenty of large cardinals flying around, right? So this will be this is basically now the first step. So we produce these T models, but at the same time, I already told you we want to code into these T models, and we want to code into these T models with objects which are of H omega 2. And which are CCC forcings. So one candidate, of course, are these Suslin trees. So what we do while going along in our iteration and producing these T models is we feed in forcings which produce constantly these Suslin trees, right? So write a big plus there. So we start this proper iteration of length alpha to produce these T models and feed in forcings to produce Suslin trees. And these Suslin trees should of course have the property that, you know, as already said, I mean, we want to produce this long sequence of Suslin trees such that whenever we take finitely many out of them and build their product, then it still be a Suslin tree. And we can do this. This is a technical lemma to check, but if we just force with the good old forcing, Yek forcing to add a Suslin tree, this will just do it. It's not so hard to show. Yes. Okay, good. Yes, and the third thing we want to have, of course, I mean, this is just producing the right ground model, but we have to take care of the non-stationary ideal being saturated as well. So what we feed in here as well is the third thing is the so-called sealing forcings, which eventually force NS, the non-stationary ideal on omega 1, to be saturated. Okay, and one has to check, of course, that all these things melt in together nicely. So it is very important, for example, to note that the sealing forcings don't kill the Suslin trees. And it is very important to note as well that all these forcings, in order to create this T model hierarchy, won't kill Suslin trees as well. So this whole iteration, whenever we add in that iteration a Suslin tree, we won't lose it for the rest of the iteration. And this is important. Because now, in the end, we will end up with lots of Suslin trees, and we can use the well order of these T models to even create a definable list of Suslin trees. Right? So what we will end up, say, after, exactly, so we do these three forcings, and we do this of length delta. So delta is our Woodin cardinal. Yes, another technical point I forgot to mention. The problem is that, okay, so the forcing to make the non-stationary ideal being saturated is in fact only semi-proper. So we can't really do a countable support iteration. We need to have an RCS iteration. And it's even worse because we want to keep the fact, we want to keep all the Suslin trees we create along the way. So we have to have, we need a Miyamoto nicely supported iteration, in fact, even. Miyamoto came up with an iteration which preserves the Suslinity of trees, right? So we need a delta, so we let delta be our Woodin cardinal. We start a delta length iteration of support, of nice support, say, and nice referring to that iteration theory of Miyamoto. Yes, and what we will end up in the end will be a W0, a big W0, which is a generic extension of V. And W0 has now the following properties. So at first, NS is saturated in there. Its H omega 2 is a T model. Using the T-ness of H omega 2, we can define in there, I mean, there is an omega 2 length sequence of independent Suslin trees. And with independent, I mean that we can, as already said, we can kill them and specialize them at will. Without losing the CCC-ness and without changing the Suslinness of the trees we left out. Suslin trees. So I think that should be it. That should get us started. Yes. Exactly. So we do have this fat model. And now over W0, we start all over again a new iteration. We start an iteration which only kills the Suslin trees now. And we kill the Suslin trees according to the stationarity of the stationary sets, right? So we do have this definable sequence of Suslin trees. We do have our stationary sets, and we start writing into the definable sequence of Suslin trees the characteristic functions of stationary subsets of omega 1. And we do this in a second iteration, which has again length delta. So in fact, we do a delta plus delta length iteration. And the second iteration will just be CCC. And the just CCC-ness will enables all these coding things. We can find the old objects and everything. I mean, there is a little bit more to work in there because, I mean, these T models, we want to use the well order of the T models to find uniquely such a sequence of independent Suslin trees. We want to, right? I mean, we always pick the least tree in the well order, then the least trees, and the least tree, and the least tree, and so on. And if we do that, then the definition won't be sigma 1. So we have to somehow come up with suitable models, suitable Aleph 1-sized models, which already are correct about the computation of the sequence of the Suslin trees. But we can do this. We can do this if we just, I mean, after in W0, over W0, we first force with an almost disjoint coding, which basically codes up the predicate for being a suitable model. And a suitable model is just a T model which computes the canonical sequence of independent Suslin trees correct, even though it just has size omega 1. It computes it correctly up to its ordinal height, right? So for that we use almost disjoint coding, and then we just write down the patterns basically of the characteristic functions of the stationary sets. So that's it.